In this video about bond enthalpy and bond length, we're going to start to think about how can we use the bonds in order to create or determine delta H for a compound. So first, let's think about O3 and bond length. If we remember our resonance structures for O3 or ozone, we had these structures where O, one of them, has a single bond connected with a double bond, and we have a positive charge and a negative charge. We also have an equivalent structure where it looks like this. And so we have these two structures. So when we think about a double bond or a double bond has 4 electrons, and a single bond has only 2 electrons. So when we increase the electron density between two atoms, it's going to decrease the length of the bond. So the length of a double bond, this bond is shorter than an equivalent single bond. So for O3, it turns out that these are neither equivalent to a single and a double. It's more equivalent to a 1.5. So somewhere the average that allows us to have this resonance structure where the two have different lengths. So these are both the same length. And they are roughly somewhere an average of a single bond and a double bond length. So let's think about this in terms of a carbon bond. So a carbon-carbon single bond versus a triple bond. So what we see when we look at just the length is that these, as we go down, they get shorter. So we have a carbon-carbon single bond, a carbon double bond, and a carbon triple bond. This one is the shortest. What we'll see in later videos in the next segments is that these triple bonds actually hold these tighter and tighter together. And we can measure that by looking at the bond enthalpy. So bond enthalpy is the energy required to break a bond. So a carbon-carbon single bond requires only 347 kilojoules. It requires more to break a double bond, and even more energy, 837 kilojoules, to break a triple bond. And this is going to be true for any bond. So as the electron density increases, the atoms get closer and closer together. So as electron density increases, the atoms get closer together, and more difficult to break. So these bond enthalpies, we can start to use that to calculate delta H. So bond enthalpy, which is the amount of energy required to cleave a bond. So if you have a hydrogen-hydrogen bond, it's going to require 436 kilojoules of energy to go from HH to 2H. So we're just snapping that bond in half. And so there are tables, as you'll see in the upcoming slides, or that you can find on the internet. So for bond enthalpy, there are 2 ways that you can think about this calculation. It is the sum of the bonds broken, so this is our reactants, minus the bonds formed, or the products. All bond enthalpy values are positive. So this minus the bonds formed allows you to make the formation negative. So the other way people write this is broken plus a negative formed. So for each bond that forms, the bond enthalpy is negative. I find that to be complicated. I prefer the bonds broken minus the bonds formed. So let's look at an example. So the first thing is we need to have a Lewis dot structure for each of these compounds. So for N2, we're going to take the valence electrons of 10, distribute those to a structure that looks like this, where all have octet, and it's going to be plus 3 hydrogen-hydrogen compounds. Everyone has octet, so we'll draw out all 3 of these. And then we're going to make 2 ammonia, so NH, H, H. You don't always have to draw out all of these, but for this first example, we will. So now we need to total the bonds that are broken and total the bonds that are formed. So we have 1 nitrogen-nitrogen triple bond, and we have 3 hydrogen-hydrogen bonds, because we're just counting this bond, and this bond. So there are 3 of them. Sometimes students feel like it should be 6 because the 3 hydrogens are cleaved, but it is specifically the number of bonds. And that's going to go to, let's count how many of these we have. 1, 2, 3, 4, 5, 6. So we have 6 nitrogen-hydrogen bonds. So when we look at the table values, we have 946 plus 3 times 436. And there's no table on this slide, but there are on the upcoming slides. Minus 6 times 389. So what we'll have here is a total of 2254 minus 2334. So delta H reaction is negative 81 kilojoules. So in order to calculate delta H reaction using the Lewis dot structures, we just need to know what bonds are present. So it's important that we practice drawing Lewis dot structures. So let's look at another example. So in this calculation, it asks us to use the bond enthalpy, and we're provided a table to calculate delta H reaction for methane plus water goes to CO2 plus 4H2. So the first thing we need to do is draw our Lewis dot structures. So I'm going to draw the Lewis dot structures of the reactants first. Once I draw the Lewis dot structures of the reactants, I'll draw the structures of the products. Once we have all of the Lewis dot structures, we can write out the bonds that are broken minus the bonds that are formed. So I like to write this, and then for all of the reactants. So we are going to start with the methane. So there are 1, 2, 3, 4 CH bonds. And then there are 1, 2 OH, but there are 2 molecules of that. So that's going to also give you 4 OH bonds minus formed. So the first thing we're going to do is calculate 1, 2. So we have 2 carbon-oxygen double bonds. And then there are 4 hydrogen-hydrogen bonds. 4 H, H. So now we can look at the tables. So we find the CH bond here, and we use this number of 4 times 414. Then we have OH, which is the next one down, and is 4 times 464. Then we have 2 carbon-oxygen double bonds. So it is 2 times 799. And our hydrogen-hydrogen bonds are here of 4 times 436. So then we can total these values up, and we get 3512 when you add these 2 values, minus over here, we have 3342. So when you subtract these 2 values, delta H reaction is equal to positive 170 kilojoules. So you have to put energy in order for methane plus water to give you CO2 plus hydrogen gas. So in order to do this, you need a Lewis dot structure and a table. So let's look at another example. So in this example, we have ethylene plus O2 gives you CO2 plus water. So first, I will draw the Lewis-Dot structures of the reactants. So for C2H4, there are valence electrons that we will donate between the two to give a double bond. So in this case, it was C connected to C, H, H, H. Then we had one lone pair here that we used here to create a double bond. Now I'm going to go ahead and draw the structures of our products. So now that we have the reactants and the products, we can actually write down the bonds broken minus formed. So we have 1 carbon-carbon double bond, 4 carbon-hydrogen bonds, 3 OO double bonds. In terms of formed, we have 4 oxygen-carbon double bonds and 4 OH. So now we can look at our table and find for carbon-carbon double is 611 plus 4 times 414. For the carbon hydrogen, for the oxygen double bond, it's 498. So then we can total all of those up and get 3,761 minus the formed. So we have carbon oxygen double bonds of 799. So 4 times 799. And 4 times OH, which is 464. When you add those together, you get 5,052, and so that equals negative 1,291 kilojoules, which is delta H reaction. So in this case, it's important that you draw a valid Lewis-Dot structure because you can't determine the delta H if you're not sure what bonds go in there. So this is how we can use bond enthalpy in order to determine the delta H reaction.